Okay, so let's see some minor improvements we have done and finished actually the whole project. So we have the game. And the game was improved a lot. So let's see what has happened. So let's go over one by one. First, the piece. So we have replaced the O and X with some fancy characters so that when you play the game, so 6, 7, Olcay, and there is also will start yes. So if you start yes, let's say you enter the index, so you see the characters are, let's say, like pieces. So it's actually a fancy scene. We only replaced the characters with some UTF codes you have seen here. Okay, that's one modification. Another modification is actually in the game. So in the game, we also added the case that the human can start or computer can start. So in that case, we ask, if, will you start yes or no? And depending on the answer, if the answer's lowercase starts with Y, which is yes or larger yes or Y, etc., then the player one will be color blue, and then the computer player will be yellow. So actually, the first player is always blue, and the second player is always yellow. So in that case, we change the color of the computer. Actually, it gives some complex issues, but the thing is, we will handle that later. So we also, that's why changed here from human to player one game and player two get name, so that it will always print the correct name. And then similarly, we modified here because the winner of the game will not be always blue or yellow. If it is blue, it's human, etc. Now we should change it. So the thing is, if the word winner of the game equals player one get color, then player one wins the game. Otherwise, player two wins the game. So these are actually the modifications we have done for the game. And then let's continue the board. So in the board, we have modified, actually, we missed one check, which is actually, we checked only up, right, diagonal. But we also should check down, right, diagonal. So in that case, we added this new method. And in the upright diagonal, we also modified this row no plus I, column no plus I, etc. So it's correct now. So for that reason, we added check upright diagonal in for a row and check down right diagonal, because since we are going up to from 0 to up, we can check like diagonal upright or check down right diagonal. Okay, so left diagonal check, we don't need because it's actually equal to the down right diagonal. And the situation is the reverse. So for the, we also implemented 3 in a row for complex evaluation function. In the 3 in a row, we calculate how many 3 pieces you have in a row. And then depending on a given color. So for a specific color, how many pieces are there? So in that case, we check the cell color and then check upright diagonal and down right diagonal, and we count them so that we don't recount the 3 in a row. So these are the modifications in the board. So then we have the computer player. The computer player now calls the state generate 3 of moves with its color, because now the computer can have 2 different colors depending on who will start the match. Okay, so let's see. Then the evaluation function should also change. because the computer color may change. It may be blue or yellow. So therefore, we modified the evaluate interface method with adding by a computer color. So now let's come to simple evaluation function and complex evaluation function. So simple evaluation function, it's like this. It checks if there is a 4 in a row. If there is no, you return 0. If there is a 4 in a row in computer's color, it returns 10. If it is not, it returns -10. So that it tries to maximize, the computer tries to maximize its score. So therefore, it returns 10 if it wins. And if it loses, it returns -10. For the complex evaluation function, we again first check if there is board 4 in a row. If there is, if the computer wins, you get 100. Otherwise, you get -100. Other than that, if it is empty, now we utilize the 3 in a row. So if the computer's color is yellow, we need more yellow, let's say 3 in a row than blue in a row. And more, otherwise, more blue in a row than, etc., etc. Okay. So other than that, we have also, we talked about the board. So let's also modify the program. Starts with what? Starts with actually with black. So in that case, black is the first color, white is the second color. Black, so we should modify black, blue for black. Okay, then can we do that? Blue for black and white for yellow. So then, so the first player will be black always. Etc., etc. So it goes like that. If I don't start, actually, then in that case, black is the computer. So let's put 1, black is computer. It puts again there, it puts again there. So let's put 3, 2, it goes like that. Okay, so that's another change. So let's go to state. So in the state, we have now modified a lot. So first of all, the generate tree of moves, which is a large method. For that reason, we shortened it by adding evaluate method, which gets the child state and the computer color. And depending on the evaluation function, it calculates its child's state score. So other than that, we also did some modifications here. So the idea is now like this. So if first we identify the color, so current color. So at this level, which color is active? So if it is first level, then computer colors will be active. Otherwise, depending on the situation, the color should be the reverse. So we have a reverse here. So the computer color is white and it's black, etc. And then we actually try to generate next states. So in that case, if the column is not full, we create a new board and child state, and then set the move there, and then add the next states. And in that case, there are two possibilities. We are at the last level. If we are at the last level, we should evaluate the child states. Otherwise, we check for each next state. If the current board is game over, in that case, we don't need to search more. We just evaluate the child state. Otherwise, we should generate more subtrees for that child state and then select after creating, select actually the minimum or maximum depending on the level. So that's actually should be done here. And then we set the score actually. So that's all. So currently it's powerful computer. So we have an expert complex evaluation function. Actually, not so complex, but the thing is, if the level gets larger and larger, you don't have any chance to win. So for level 4, actually we can play until 6th level. So the 6th level, it plays fast. So it's just 1 second. Not just 1 second. So let me start first. So if I put, it directly puts. So as you see, put, it plays as fast as possible. So if the level is 7, but if the level is 7, so in that case, it's a little bit slow. So do we need that? That's another discussion. But so we are waiting now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. So you see it plays. So at the beginning, it plays actually a little bit slow because the alternatives are too many. So when the game continues, it gets a little bit faster. So 11. So you see now it finds. So we can actually create a timer, how many seconds it requires. So let me add the 6. As you see, it closes the gap. So it directly responds. So if it finds that, other than that, I will lose, then it directly plays that game. So for 7, it is playable actually, 10 seconds or 5 seconds, but it's very strong. So in that case, so we can actually make this a little bit better, but we will stop actually here. So level is 6.